Frostbite Theater presents Cold Cuts, no baloney.
Just science.
Hi, I'm Joanna.
And I'm Steve.
Usually, every couple years, Jefferson Lab hosts an open house. This is the one time the public can come and tour our accelerator and end stations.
During the 2010 open house, our cameraman snuck into one of the ongoing cryo shows that are held throughout the day. He missed half of it. So if you want to see the entire thing, check our website to see when the next open house will be.
Until then, enjoy!
Who would come down and stick their hands in? Okay, but before we do that, the two of you put on goggles and put on gloves. While they are getting goggles and gloves, what are these? Flowers. These are the flowers of science. Are these hard, soft, real, fake?
They're real.
Okay, the nice people on this part of the front row says that they are real. Do you trust these nice people? More nice people. These are nice, real flowers. They're nice and soft. What I propose to do, before we have our volunteers put their hands in the knife and possibly get hurt, I say we put the flowers in first. If the flowers turn out okay, then we'll make them put their hands in. Is that fair? Yeah. Good. What is taking you so long? Whoops. There you go. That's the whole point of the goggles, so you can't see. Okay, which one do you like? Good, which one do you like? Your choice. Ladies first, come on over here. Stand right over here. Hold the flower at the very end of the stem. And when I tell you to, very slowly, you okay? Okay. Very slowly and very carefully put the flower into the nitrogen. Everyone else listen, see if it makes a sound. It's like a sizzling toilet flush. Why is it making that sizzling sound? What's boiling? The nitrogen, because the flower's too hot. The flower's room temperature. And it goes to the nitrogen. Nitrogen goes, that's a really hot flower. The nitrogen boils, goes in the air. We end up breathing this stuff. Very carefully take it out, please. And hand it to me. Is the flower okay? No. It still looks like a flower. It's just a little bit foggy, but that's okay. Like, you stand right over here and face down. I'm going to hold this over here like this. And you take your hands and squeeze that nice soft flower. Squeeze. Squeeze. Yeah. Okay, you hold this. Now, in science, normally don't do an experiment just once. Right? Do an experiment once, when weird happens, you don't know if that was supposed to happen or if it's her fault somehow. So, we take a few steps this way. You come in over here with the emergency backup flower. Stand over here. Same thing. Carefully put it in. It's making that same sizzly sound. And if you can't hear it, you can at least see there's more fog that comes out. Because again, when it makes the gas, it's got to go somewhere, so it spills out of the container. Carefully take it out, please. Same deal. You stand over here. I'll hold it. And you squeeze. Wow. Yeah. You hold this. Now then, what happened to the flowers? Why did they break? What froze? What in the flower? What are the petals? The water. There's a lot of water inside the flower. The flower is like 70-80% water. They shoved the flower in there, all the water froze, turned to ice, and when they squeezed it, instead of being a liquid, being able to flex, it was a solid and it broke. Do our brave volunteers have any water in them? Yeah, your body's mostly made out of water. What would happen if they were to shove their hand in here? Yeah, same thing. All the water, all the blood in their hand would freeze. If they took the frozen hand and kind of whacked on the table, you'd have little bits of hand on the table. So, should they put their hands in? No, they should. Give me a hand for helping us out with big hand. Put these over here so nobody notices that they're hurt. I'm going to need two more. Two more brave and slightly foolish. Oh dear. No one ever wants it. The lady with the blue Jefferson Lab bag. And the lady in the white sweater with her little hair like this. Oh, put the other one in here. It's much shorter this way. Goggles and gloves. And it's almost out. Almost. Should have just thrown her over. Perfect. Goggles and gloves. Oh dear. Anyway. are getting goggled and gloved. What are these? Balloons filled with? Air. Just air. If they were helium, go really high, be hard to use. What are we going to do with these? We're going to stick them in the nitrogen. What's going to happen? We're going to pop, of course. Which one do you like? Which one do you like? Good choice. Tell you what, you stand right over here. And you stand right over here. Hold the balloon by one end. At the count of 3, you're both going to put the balloons into the nitrogen at the same time, but not your hands. I'm going to stand way back. So, give us a count. 1, 2, 3. Put them in. Have they popped? Keep pushing. Ooh. Keep pushing. What's happening? That's not good. Not good. Tell you what, you let go of this one, and you let go of that one. That's not good. Do the balloons have any air in them? Well, choice or yes and no, right? Maybe instead of popping, maybe the balloon just got really cold and it cracked an egg. And then all the air leaked out the crack. If it's true that the balloon has a hole in it, and the air is gone, when we take the balloons out, what will they do? Balloon with a hole in it, it's going to stay the same. Who says the air is in there? If the air is in there, where is it? Okay, so if we take it out, let it get warm, what will happen? Okay, 2 different theories, 2 predictions. What should we do? Gotta try it out. Grab your balloons. Hold them up high so we can all see you, please. Shake around, do a little balloon dance. Shake. Now, let me see this one. Are the balloons okay? Do they have holes in them? Did the air leak out and then go back in? So what's going on here? Tell you what, this is the open house. We're not going to demonstrate it with those little wimpy balloons. I'm going to put this in. If I put this in here, what's happening to the temperature of the air in the balloon? It's getting colder. What did we say earlier happens to the particles of the gas when they get cold? They slow down, they take up less space. If you get them cold enough, you can change them from a gas to a... And I claim that's what we're doing. I claim we're getting this cold enough, we're taking all the air, all the oxygen, all the nitrogen, and we're changing it from a gas to a liquid. If that's true, what should we see in the bottom of the balloon? We should see a liquid. It's going to be hard to see, so I'm going to kill the lights part way. I'm going to hit it with a flashlight. In the very bottom of the balloon. What is that little puddle in the bottom of the balloon? That's air. That's a little puddle of liquid oxygen and a little puddle of liquid nitrogen. If I shake, you can even hear it. And if I keep shaking it, it goes away, right? Because it all boils again, changes back to a gas. So, party tip. Next time you have a party with a lot of balloons, at the end of the party, don't throw the balloons away. Just get some liquid nitrogen. And you can shove the balloons in. And all the air inside the balloon will change from a gas to a liquid. And then the next time you want to have a party, instead of blowing up a bunch of new balloons, you take the old ones out. Put them somewhere hot, like the table. And then the liquid air inside will boil. Sometimes they pop, just be aware. And if all goes well, the balloons survive. Sometimes they pop. And you can have another party. So a hand, please, for our brave volunteers. Now, I'm going to do the same experiment they did, but backwards. Okay, instead of taking air, trapping it and getting it cold, I'm going to take the liquid. I'm going to put it in these little film canisters. And I'm going to trap it. And I'm going to let it get hot. And once these are cold, we'll snap the lids in place. Whoops. Uh-oh. Get on. What's going to happen? What's going to happen? Why do they pop? Where's the pressure coming from? If you remember the balloon, right? make a balloon's worth of air, right? It can't fit. Sooner or later, the pressure goes too high and the lids pop off. Also remember that as soon as I put the lids on, nothing new goes in. Same amount of stuff. But some of it is changing to a gas, it's able to hit the lid, and the stuff that is hitting the lid is moving faster and faster because it's getting hotter. So sooner or later, so much stuff hitting the lids that the pressure goes too high and the lids pop off. Now, remember my big tank. My big tank has a lid. If I do this, and then I do this, what's going to happen? Why nothing? Yeah, this is more like a hat. This isn't really sealed on. That's on purpose. But you don't want the gas building up in here. A little film canister going pop is kind of cute. A real thing like this going pop is going to go through the ceiling, which they yell at you when you do that kind of thing. So, what is this? Yeah, it looks like a rocket. This is actually a magnet. And it's a little bit weird of a magnet because it plugs directly into the outlet. And I don't know if you know this or not, but the electricity you get from the outlet changes direction 60 times a second. So when the electricity is flowing this way through the magnet, this becomes the North Pole. When it flows this way through the magnet, this becomes the South Pole. So the north and south of this thing are flipping back and forth 60 times a second. What's this? It's actually a copper ring. Does copper stick to a magnet? No. If I turn that on, it doesn't stick, but if I place it on, it floats. And if I turn it off, it falls. If I turn it on real fast, it flies off into the air. Right? That's because the magnetic field made in this ring from the changing magnetic field here. Right? Changing magnetic field makes electricity run around this ring. This becomes an electromagnet. And the way the math works out, whatever pole that is, that's the same. So it's always sitting here up in the air, but it doesn't really go all that high. That's because the ring has a fair amount of resistance, which means the electricity that's flowing through the ring can't flow as well as it could. I can fix that using a tiny bit of nitrogen. So put a little bit here. Right, resistance acts like friction for electricity. And sometimes it's good. Right? You use it to change electrical energy to heat. That's why your toaster works. Right? But a lot of times it's bad. It's just wasted energy. But if you get a conductor cold, you can lower the resistance. And if you lower the resistance, the electricity will flow better. If the electricity flows better, how will it jump? Should jump higher. Now, some materials get them cold enough they lose all their resistance. Those are called superconductors. That's what we have inside our accelerator. Right? We use liquid helium to make these things called niobium cavities, which you'll learn about when you go out there. We make them superconducting. Mostly so that we don't generate waste heat. And in part, that actually saves us quite a bit of money. Right now, we pay about $1 million a month in our electrical bill. If we had regular things that made heat, our electric bill would be about $10 million a month. So just by using superconductors, we can save about $9 million a month in electrical bills. Now, this is not a superconductor, but it's a better conductor now. We're expecting to go higher into the air. Front row, I don't always catch these things. If the ring comes towards you, don't grab it. If you grab this thing when it's cold, frostbite in about half a second. Okay, remember how high I went before? See if it's any better now that we've lowered the resistance. Not too bad. And if we turn it on at the right time, we can actually hit the ceiling. Not a superconductor. There's still some resistance. I have some frost in the ring, and I hold the ring in place. The heat made from the electricity brings us above the freezing point, and the frost just vanishes off the ring. Then I can hold it and not get frost there, which is nice. Now, who's ready for a quiz? Who's not ready for a quiz? Best time for a quiz, when you're not ready. It's not a hard quiz, so don't panic unless you like to panic. It's not going to help you. Question number 1. What is this? What kind of ball? Ping-pong ball. And this is how a ping-pong ball bounces. It's insanely exciting. What's this? Bouncy ball. That's how the bouncy ball bounces. Uh-oh, come back. What's this? Racquetball. That's how the racquetball bounces. All of this insanely exciting. We'll let those get cold. Jefferson cup. It's not made out of little bits of Jefferson, which would be gross. It's made from a metal called pewter. Pewter is a soft metal. Soft in that if I squeeze it, I can change the shape fairly easily. Okay? Now, since this is so nice and soft, it makes a beautiful sounding bell, doesn't it? No. Not really. But you know, it's all smushed. There's another one here that's not smushed, and this one's slightly shiny. This one makes a beautiful sounding bell, doesn't it? No. Not really. How can I make these ring better? Sure, I can get nitrogen into these cups either the easy way or the hard way. Which would you prefer? I personally say easy way. No one thinks it's easy. Anyway, it's the same way, so you don't actually have a choice. It's a little bit there, a little bit there. A little tiny bit on the table. Now then, while these get hold, where's that one? Stay. Let's see how these guys are doing. Which ball? 321 degrees below zero. You're going to bounce the metal plate. What's it going to do? Break. It's going to break, of course. Ready? Actually, kind of a boring experiment. Nothing really happens. But nice to know some things can get really cold and they don't care. Right? If you're going to build a machine that like we did that passes around when it's cold, you need to know which materials are good and which aren't. Turns out ping-pong ball, really not all that bad. Question number 2. What ball is this? 321 degrees below zero. Now bounce the metal plate. What's it going to do? Break. Break, of course. Ready? Yeah. Not a very good bouncy ball. Hard as a rock. Maybe not that marble now, but not a very good bouncy ball. Question 3. What ball is this? 321 degrees below zero. Now bounce the metal plate. What's it going to do? Break. Now it said break for everything. Something's got to break, right? Ready? Yeah. That kind of broke. So, the lesson to take from this, if you ever go on vacation somewhere where it's really, really cold, somewhere like Pluto, okay? Go ahead, bring ping-pong balls. You can play ping-pong on Pluto, not a big problem. Go ahead, bring the bouncy balls. Use them as marbles or small rocks or something. And if you ever want to play a game of racquetball on Pluto, make sure you serve first. That's it. Now then, the bells. What did this first one sound like when it was warm? Yeah, kind of a thud. Let's see if it's any better now that it's cold. It's better. It's not great. It's still smushed. It's still not shiny. This one, not smushed, shiny. Not too bad. We took the pewter inside the cup, froze it rock hard. Hard things were better than soft things do. That's why your pillow doesn't rain at night when you put your head against it. The little bells also signal the end of our little show here, but it's not the end of the day. There's lots more open house to do. Right? So go to the tunnel, go to the inside. There are other places in here. You have a computer center tour, other stuff in this building. Thank y'all for coming to the house.